All right, Algebra 2 Trig. This is probability section 3. We're going to go over some basic probability rules and set notation and then do some probability problems. So our objectives are to interpret set notation through symbols and the use of Venn diagrams. We will state what the general addition rule is and recognize what mutually exclusive events are, and we will work with Venn diagrams and two-way tables to apply the general addition rule. And so like with other videos, if you need to start, stop, go back, feel free. We can use Venn diagrams to illustrate the sample space of a chance process. We will also be using set notation to express probabilities, so you will have to learn to recognize them, not just the sets themselves, but also the symbols and the notations that go with them. So first we have the union of sets. So we have two sets. We have set A, represented by the circle on the left in the Venn diagram, 1, 2, 3, and 4, and we have set B, 3, 4, 5, and 6. The set 1, 2, 3, 4, 5, 6 consists of all the elements in at least one of the sets A and B. So this is called the union of A and B. This is indicated by the symbol U, that round U. So what the union is, it's basically combining the sets together. Now it turns out some of them overlap, like the 3 and 4 are both sets A and B. So they are placed in the middle. But if you combine the sets into one, you don't repeat those elements. So 1, 2, 3, 4, 5, 6 represent the union, the putting together of sets A and B. If A and B are any sets, then the set whose members are the elements belonging to A, B, or both is called the union of A and B. This is denoted by AUB, where the U represents the meaning of the word or. So or A or B is the same as uniting A and B together. Okay, so uniting them, or A or B, A union B, same thing. And that basically is the combination of all the elements that are in either of the two sets. So event AUB is the set of all outcomes either in A or B. It's the equivalent to the event A or B. So this union symbol, that U, is the same as the word or. So when you think or, it doesn't mean A or B, but not both. It means in A or in both B, or in both. So keep that in mind. It's not truly literal. Or can be in either, or both, or all of the sets. The intersection is the common elements between two different sets. So you can see sets A and B. They have two common elements. 3 and 4 are in both sets A and set B. Since sets A and B are subsets of W. W is the set of whole numbers. That's the numbers 0, 1, 2, 3, and so on. The overlap, here set 3, 4, is called the intersection of A and B. You can see in the diagram how the two circles intersect. And they intersect with the contents 3 and 4 because 3 and 4 are in both sets. The symbol, that upside down U, represents an intersection of sets. We say the intersection of sets 1, 2, 3, 4 and 3, 4, 5, 6 are the elements 3, 4, because those are the elements that are in both sets. If A and B are any sets, then the set whose members are the elements belonging to A and B is called the intersection of A and B. This is denoted by the intersection of A and B using that symbol. It looks like an upside down U or a rounded N. That symbol is the equivalent to the word and. So you say A and B, that means the elements that are in both. So the event A and B is the set of all outcomes in both events A and B. And you can see on this Venn diagram, it's that green section in the middle. So if you think of it this way, you have freshmen and women, freshmen and girls. If A is freshmen and B is girls, the intersection would be freshmen girls. The empty set, symbolized by that 0 with a slash through it, is the event without any outcomes in it. So the intersection of A and B is the empty set, the null set. Another word for this is called disjoint sets. The sets 1, 2, 3, 4, and 5, 6, 7, 8 have no elements in common. So the intersection of those two sets is the empty set. Sets that have no common elements are called disjoint sets. In other words, there is nothing that they jointly share. They are also called mutually exclusive. In other words, they have no elements in common. Remember, mutually exclusive events we discussed in our last lecture, that two events cannot happen at the same time. So, graphically speaking, the events A and B are mutually exclusive if they don't overlap. And you can see these two circles, A, B, have no intersection. So again, think A might be juniors, B might be sophomores. there is no overlap between them, unlike the previous example where I said A was freshmen and B was girls. There's overlap. With juniors and sophomores, there is no overlap. There are no students that are in both sets. They have no outcomes in common. The last term for now, the complement. You will see this symbolized AC. In our book, you will see it symbolized as an A with a bar over it. It means the same thing. The complement AC contains exactly the outcomes that are not in A. So the union of A and AC is S, where S is the sample space. It is all elements. The intersection of A and AC is the empty set. So think might be, in this case, A might be freshmen. AC would be all non-freshmen. So you notice, you put them together, you have all the students in the school, the sample size. If you look for people that are both freshmen and all the students that are non-freshmen, there is no overlap. So that is the empty set. The intersection is the empty set. All right, let's work through some of these examples. Example 1, specify each of the following sets by roster referring to the Venn diagram. So first, A, we have the intersection of A and C. So you want to look for the elements that are in both sets A and sets C. And to do that, you can see it's the 8 and the 10 that are in both. Next, we have the union of sets A and C. So you want to look for the elements that are in either A or C or both. So if you put those in order, you end up getting 0, 1, 2, 4, 6, 8, 10, and 11. You don't have to list them in order. It just makes it easier to sort through it. All right, so I would like you to try a couple of these in example 1 and stop the video. When you're ready to resume, restart it. All right, C, the intersection of sets B and C. You want to look for the elements that are in both B and C, and that is elements 0 and 10. D, the union of sets B and C. You want to look for the elements that are in either B or C or both. That comes out to 0, 2, 3, 4, 8, 9, 10, and 11. The intersection of sets B and D, they have no elements in common, so that is the empty set. F, the union of A and B intersected with C. So you're going to want to follow the parentheses as the order of operations, do the first one. So the union of A and B is 1, 6, 4, 10, 8, plus 0, 3, and 9. You want to see how many of those intersect with C, and those are just 0, 8, and 10. So you think of A or B as one large glob, and think of among those elements, which of those are also in C. That leaves you with 0, 8, and 10. All right, we're going to go through some basic probability rules, and these are universal rules no matter what you're studying. So you should also learn how to interpret the formal mathematical notation. All of the rules are intuitively true facts about long-run proportions. So remember, probability is a statement about if you were to do this forever, what would that theoretical probability be? So if A is an event, we will write the probability as P parentheses A. So P refers to probability, A is the event, so P of A. So first rule. Any probability is a number between 0 and 1. So 0 is less than or equal to P of A is less than or equal to 1. So an event with a probability of 0.5 occurs in half the trials in the long run. Rule number 2, the probability of all the elements in the sample space equals 1. All possible outcomes together must have probability 1. So if S is the sample space in a probability model, then the sum of probabilities for all the outcomes must equal exactly 1. So any of the outcomes, the probability of any of the outcomes showing up is 1. Rule 3, the probability of the complement is 1 minus the probability of A. Likewise, the probability of A plus the probability of the complement of A equals 1. So AC refers to the complement of event A. Notice complement is spelled with an E, not complement, which is something nice you say to somebody. The probability of an event and its complement add up to 1. So basically the probability of an event happening plus the probability of the event not happening have to equal 1. So if an event occurs in 60% of the trials, then it has to fail to occur in the other 40% because those two numbers equal 100%. This rule will come in handy as you try to do some of the more complicated probability problems, keeping in mind that the probability of an event not happening is 1 minus the probability that it happens. So the probability you will go to prom is 20%, then the probability you will not go to prom is 80%. Equally likely outcomes. If a sample space S has n equally likely outcomes, then the probability of each simple event is 1 over n. When you roll a die, there are 6 equally likely outcomes. The probability of each is 1/6. If you draw a random card, the probability of getting any one card is 1 out of 52 because there are 52 cards. If you flip a coin, the outcomes are heads or tails, so the probability is 1/2, 1/2, because there are 2 events. So the probability of an event. To find the probability of an event A, you can count the number of ways A can happen, and you divide it by the total number of outcomes in the sample space. So the P of A equals the number of outcomes that A can happen divided by the total number of outcomes. So on lesson 2, we looked at permutations and combinations. Those gave us the number of possible outcomes. We can do similar things to find the number of outcomes that satisfy event A. We divide those two to get the probability. So let's take a look at example 2. A red and a green die are rolled. Let's call rolling a sum of 6 event A and rolling a 4 on the green die event B. So the first thing we want to ask is, how many possible outcomes are there for the roll of 2 dice? And as you can see from the chart, there are 36, 6 times 6. So that's going to be the total number of outcomes. For all our problems in this section, it's going to be something divided by 36. Let's take a look at 2A. What is the probability of A? In other words, what's the probability of rolling a sum of 6? Well, you want to count how many ways are there to roll a 6 in total. And there are 5 ways. 5, 1, 4, 2, 3, 3, 2, 4, and 1, 5. So there are 5 total ways. So to get the probability of rolling a sum of 6, you take the total number of ways and divide it by the total number of outcomes. So P of A equals 5/36. Example 2B, what is P of B? Well, again, you want to count how many outcomes have a green 4. And there are 6 of them. There they are. So the total number of outcomes is 6. You're going to divide that by the total number of outcomes, which is 36. So 6/36 equals 1/6. So 6 represents the total ways to get event B. 36 represents the total number of outcomes. 2C, what is the sum of not rolling a sum of 6? Well, instead of counting all the ways you don't roll a 6, what we can do is look at the complement of rolling a 6, because that would be the opposite of rolling a 6. So rolling a sum that's not a 6 is 1 minus the probability of rolling a 6. So that equals 1 minus 5/36, which is 31/36. So you see how the complement works. Sometimes it's easier, instead of counting all the ways something can happen, count up the ways something cannot happen and subtract that probability from 1 to get the probability you want. 2D, what is the probability of the intersection of A and B? In other words, what's the probability of rolling both a sum of 6 and the green die is a 4? So what you can do is look at the chart to figure out how many ways can you roll a 6 and get a sum of 4, and it turns out there is only one way. So the probability of rolling an A and B, a sum of 6 and a green 4, is 1 out of 36. The other ways to roll a 6 don't have a green 4. The other ways that have a green 4 don't add up to 6. 2E, what is the probability of the union of A or B? So we want to count the number of ways we get either a sum of 6 or the green die to be a 4. So you see, those are the 5 ways to get a sum of 6 or the green die to be a 4, including the one that we use to get a sum of 6. There are 10 total ways to get a sum of 6 or a green 4, which reduces to 5/18. Notice that the red 2 and the green 4 show up twice. You can't just add the probabilities together because you have an overlap. We'll look at that more a little later. 2F, what is the probability of the complement of B? In other words, what's the probability that the green die is not a 4? So find the probability that the green die is a 4, subtract that from 1. These are the outcomes where there's no green 4. It's 1 minus the 1/6 we got in example 2B, so the probability is 5/6. All right, 2G. By the way, you can try these at home on your own to see if you get the right answer. What is the probability of A and not B? So we need a sum of 6, but we cannot have a green 4. So you want to figure out all the ways to get a 6, but not have a green 4. There are the ways to get a 6. We eliminate that one because it has a green 4, so we get 4 possible ways out of 36, which reduces to 1/9. So we want a sum of 6, but we do not want the green die to be a 4, so that leaves us 4 possible ways for that to happen out of 36. 2H. Now suppose event C is rolling a 6 on the red die. What is the probability of both happening? A and B. So we looked at that already. How many of those have a red 6? None of them. So these events are mutually exclusive because they can't happen at the same time. So for 2H, what's the probability of getting A? It should be A and C, not A and B. It should be 0. So change this B to a C. That makes more sense. So the probability of getting a sum of 6 and a red 6 is 0. All right, that's 0. 2I, what's the probability of rolling a sum of at least 10? So you want to count the ways where you can get a sum of at least 10. So you can get 10, 11, or 12. Those are the 6 ways to do it. So the probability is 6 out of 36, or 1/6. What's the probability of rolling exactly 1/3 or 1/4? So these are the ways to get exactly 1/3. We're going to now also add the ways to get 1/4. So those are the ways, and there are 18 out of the 36 rolls have at least 1/3 or exactly 1/3 or 1/4. Notice we don't count the double 3 and we don't count the double 4 because that would not be exactly 1/3 or 1/4. So the remaining outcomes equal 18. 18 out of 36 is 1/2. Let's move to example 3a. A spinner is divided into tenths. The sections are numbered 1 to 10. If the spinner is spun, find the probability that the number you get is a 2. So you want to think about how many possible outcomes there are, and there are 10 of them, and these are equally likely. So if 2 is one of the possible outcomes, the probability of spinning a 2 is equal to 1 over 10. This is the equally likely outcomes. So we can use this to get the answers to the rest of the problems in 3a, 3b, 3c, and 3d. 3b, find the probability that the number is a multiple of 4. So which are the multiples of 4? Between 1 and 10? Well, that's 4 and 8. So you want the probability of rolling a 4 or 8. There are 2 ways to do that. So the probability is equal to 2/10, which is 1/5. I will add this in this section. And probability, it doesn't bother me if you do not reduce your fractions because the unreduced fraction actually gives you a better indication because it tells you all the possible ways divided by all the possible ways something can happen divided by all the possible ways altogether. So if you don't reduce your fractions in this section, that's fine. 3c, find the probability that the number is between 0 and 30. Well, which of those outcomes in the spinner from 1 to 10 are between 0 and 30? That is all 10 of them. So the probability of getting any of the 10 numbers is 10 out of 10 or 1. In other words, you are guaranteed to spin a number between 0 and 30. On the other hand, what's the probability that you will spin 1/2? Well, that can't happen. You cannot spin a fraction. So there are no ways to do it. The probability of spinning 1/2 is 0. It is impossible for it to happen. All right, for section 4, we're going to take a look at a deck of cards. And instead of using a full deck, we're only going to use 26. So 13 hearts, 13 clubs. In case you don't know what they look like, there they are. So we're going to randomly draw a card, and we're going to find the probability that we draw a king. So how many of those 26 cards are kings? That's what you want to count. There are 2 of them, the king of hearts and the king of clubs. So the probability of drawing a king is 2 out of 26 or 1/13. Okay. See if you can stop and do these if you want. That way you can try them yourself. 4b, what's the probability you'll pick a diamond? Well, since you're only picking hearts from hearts and clubs, none of the cards are diamonds. So the probability of getting a diamond is equal to 0. There are no diamonds in your half deck of cards of hearts and clubs. What's the probability that you will randomly draw a club? Well, you have 13 clubs out of the 26 total cards, so your probability is 13 out of 26, or 1/2. Okay? And if I asked you about a spade, that would also be 0. 4c, what's the probability that you will draw a 7 or an 8? Remember, you're only drawing 1 card. So you have 4 possibilities. There are 2 7s, the 7 of hearts and 7 of clubs, 2 8s, the 8 of hearts and the 8 of clubs. So you have 4 possible outcomes out of total of 26. So that reduces to 2 out of 13. 4d, what's the probability you will draw a red ace? So among those 26 cards, how many of them are red aces? Well, there's just one of them, the ace of hearts. So the probability of drawing the ace of hearts out of 26 cards is 1 out of 26. Since you have 1 ace of hearts out of 26 total cards. All right, 4e, what's the probability that you draw either a heart or a 10? So what you want to do is think about, are the events mutually exclusive? They are not. You cannot add the outcomes together because there's going to be some overlap. So the first thing you want to ask is, how many hearts are there in the deck, the half deck of cards? Well, there are 13 of them. Now, how many of those 10s are not hearts? Because we already counted the 10 that's a heart. We don't want to double count it. So there's only one other 10 that's not a heart. That's the 10 of clubs. So there are 14 total outcomes to get either a heart or a 10, or both. So that's 14 out of 26, which reduces to 7 out of 13. So when you have non-mutually exclusive outcomes, when you add the outcomes together, you have to make sure that you do not double count things that occur twice. For F, finds the probability that it is a club and a heart. Well, if you draw only one card, it is impossible to draw a card that is both a club and a heart. So they are mutually exclusive events. The probability of two mutually exclusive events happening at the same time is 0. Now, if I ask you a club and a 7, well, you can have a card that's a club and a 7, but you cannot have a card that's both a club and a heart. All right, socks. A drawer contains 8 brown socks and 6 black socks. If 2 socks are randomly drawn, what is the probability that they match? So what you want to think about is how many ways you can get matching socks. So what are the total possible outcomes if you draw 2 socks from a drawer of brown and black socks? Well, first of all, how many outcomes are there? You're taking 14 socks and you're choosing 2 of them. It's a combination because the arrangement doesn't matter. So 14C2 comes out to 91. So what we need are either 2 black socks or 2 brown socks. So you might want to think, how many outcomes have 2 brown socks? Well, how many brown socks are there? There are 8 of them. We need to pick 2. So there are 8 C2 ways to pick 2 brown socks. That comes out to 28. How many ways can we pick 2 black socks? Well, there are 6 black socks, and we need to pick 2 of them. So that's 6C2. Again, the order that we pick the socks doesn't matter, so we're using combinations. That comes out to 15. All right, so what do? We have 2 blacks or 2 browns. Can we add those number of outcomes together, and why? And the answer is yes, because they are mutually exclusive events. If events are mutually exclusive, you can add the outcomes together. That's what we learned in probability lesson 1. So we can add the ways to get black socks. We can add the ways to get brown socks. Together, 28 plus 15 is 43 out of 91, because you cannot get both 2 black socks and 2 brown socks at the same time. So the probability, the answer 5A, is 43 out of 91. Finally, what's the probability that there is at least 1 brown sock? So the way you want to think about this is there are 4 possible outcomes for socks that you draw socks out in order. Brown, brown, black, black, or black, black. What you want is to not get 2 black socks. So we can add up the ways to get the first 3 scenarios, or we can find the number of ways to get the black, black socks and subtract that from 1, because we can find the complement of black socks. That's at least 1 brown sock. So those 2 have to add up to 1. So we already calculated the probability of getting 2 black socks, or the outcomes to get 2 black socks. There are 15 ways out of the 91 total outcomes. So the probability of getting at least 1 brown sock is 1 minus the probability of getting 2 black socks, or 1 minus the probability of getting no brown socks, which is 15 out of 91. Comes out to 76 over 91. All right, this is 23.5 minutes long. It's a long video. If you need to go back and listen to things, that's fine. In class tomorrow, I won't be here, so you'll have a chance to work on the problems. If you have any questions, you can save them for me when I come back.